To one and all present here. I, Adasha, the anchor of today's event, would like to extend a warm welcome to you all wholeheartedly to the International Workshop on Recent Trends in Computing and Mathematics 2023. This is a 5 days program which started from the 18th of August 2023 and is continuing till the 22nd of August 2023. And now we are successfully conducting our final day seminar. This is simply a golden opportunity to get to learn a bountiful of information and knowledge. This is not just a workshop, but also an amazing interactive session where the students get to rack through their brains and ask away their queries and have loads of fun while learning. We are highly honored to have such a distinguished group of guests here with us today, including professors, researchers, young students, and our college dignitaries present here with us today. We are highly privileged to have with us our guest of honor with us today. And now, I would like to introduce our esteemed guest faculties. On such an amazing note, let's begin the event with the virtue of melody. So I would like to call Pooja Pratyasha Devi to present a blissful song on this perfect day. Thank you. गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि.
So thank you for such singing for such a wonderful song. With this melodic note, we are going to begin session 1 of today's program. Ladies and gentlemen, a warm welcome to this vibrant event. On behalf of the VSSUT Burla, I would like to extend a warm welcome to Professor Costanza Conti to our campus today. She is a highly accomplished scholar and researcher in the field of mathematics. She is currently working as a professor in the Department of Mathematics of University of Florence, Italy. She has published extensively more than 80 science journal papers and books. She also has 8 school journals and co-organizer of more than 15 workshops and international conferences, 15 mini symposia, invited lecture for more than 20 conferences and 10 mini symposia. There are that interest her, one of which is numerical analysis. Her talk is based on these lines. We are honored to have her with us today to share her insights and expertise with us, adding to a valuable learning experience for all of us. So now, without further ado, let us welcome a graduate to this event with cheers everyone.
Hello. Hello, ma'am. Am I audible?
ऑडियन्स कळलं
Okay, so I hope now you can see the presentation. Can you confirm that you see the presentation? Hello? Okay, sorry, because I have no feedback. So, okay, so first of all, good afternoon, good morning from my side. I'm Costanza Conti from the University of Florence in Italy. Of course, I want to start by thanking the organizer for giving me the opportunity to present my recent results in this workshop. Thank you very much. And the presentation I'm giving today concerns recent results on a special class of spline that we call HB spline, and you will see why shortly, that we can use for data representation. This work is done in collaboration with Rosanna Campagna, a colleague of mine from the University of Campania in south of Italy, and it's kind of what I'm presenting today, kind of summary of several papers that have been recently published. So I guess that in this context you are aware of the notion of spline. We know that they are used in several contexts, ranging from computer-aided geometric design to more modern contexts, like, for example, activation function in deep neural networks, but also they are very much used in statistics, for data analysis, for the creation of some regression models. And this class of function was introduced by Schoenberg around the 60s. Schoenberg used this special class of function in several different applications, for example, in quadrature rules, like you see here in this paper, or in cardinal interpolation. And since the work of Schoenberg, a great impulse to spline was given by the work of two mathematicians working in the United States. Both are of German origin, Larry Schumacher and Karl Bohr. They contributed a lot in the field, and in particular they wrote two important books. So this is the book of Schumacher, and this is the book of Bohr, that are still an important reference for people working in this domain. I mean, every time I read the theoretical result, I check on the book, for example, that Schumacher. And if you just Google the word spline, or you put on a database like, for example, Scopus, that you see here in this picture, you see that there is a continuous increase of papers, publication in general, that appears with the word spline in the title, which means that this is a topic still very much investigated. We can say that there is a big variety of spline. So some people refer to the different type of spline as species of spline soup. And in fact, there are polynomial splines, exponential splines, rational splines, subdivision splines, Chebyshev splines. And the different type of splines find application in different contexts. For example, exponential splines in image analysis, rational in data approximation, and so on. And my personal interest in splines is essentially twofold. I use them to create exact data in some particular context, or to smooth noisy data. Here you can see some pictures just to give an idea of the difference, or in general to follow the behavior suggested by the data, and this can be in the noisy or exact situation. And relevant to all uses of spline that I have considered, I have to put in evidence already now that it's very crucial that every spline space possesses an optimal basis. With optimal basis, I mean a basis that consists of bell-shaped functions that are non-negative and compactly supported. And quite often, they also satisfy the partition purity, but this is not a property of satisfy. Here in this picture on the right, you can see the classical optimal basis for polynomial splines. So here we have linear splines, linear B-splines, quadratic B-splines, cubic B-splines, and the fact that they do satisfy partition. And what is important to observe that whenever we define an optimal basis, we need to set the knots of the basis, the points that are the breaking points of continuity that are needed to construct the function that define this. And the knots is something that I will talk about in this talk. Okay, now, how can we use a spline space to approximate the set of data? Now I'm talking in general about any spline space. The first possible way is to construct a least squares spline. So we take a linear combination of the element of the function, so the optimal base in general, and then we use we solve a minimization problem, searching for the specific spline that minimize the error with respect to the data. Now, pay attention that here we have a certain number of bases that depends on the dimension of the spline space, and a different type number of data. And this means that the nodes of the splines depends on the degree or the dimension of the space. But the idea is always the same, so we add this penalty term, we take a general spline, and we minimize the sum of the error plus the penalty term. Here, it turns out that the spline, so the solution of the minimum problem, is such that the knots of the splines coincide with the shifts of the data, and that and therefore there's no longer the need to select the nodes of the spline. Yes, but we still need to select the smoothing parameter. These are advantage and
penalty term that which is simpler, and this is the case of P splines. P stands for not only for penalized but also for polynomial splines, because P splines were the first introduced and deal with the space of cubic polynomial splines, are the solution of a penalized least squares problem of this type, and the minimization is done with respect of the splines coefficients. Still, we need to select a regularization parameter or smoothing parameter and the number of knots. So we see that here we have the number of data, and here the dimension of the space, which correspond to the number of knots. So this is the notion of P-spline, and this notion was proposed in 1996 by two statisticians, Ehlers and Marx. And just to summarize, I can tell you that they are based on essentially four ingredients. The first one is, as I said, the space of cubic splines, and the optimal base for the space that we know is the space, the basis of polynomial cubic B-splines. The knots for this basis are always assumed to be uniform, and this is a great simplification of the model. Then the model uses the fact that whenever we take the derivative of a linear combination of cubic B-spline, we end up with the linear combination of linear B-splines with a suitable linear combination. And then, of course, another crucial ingredient is a certain level of approximation. The work done by Ehlers and Marx led to important developments in data regression through splines. In fact, P-spline have a number of useful properties that is important are all inherited from the good properties of the B-spline. And these are the fact that they fit exactly constant and linear polynomial data. So if we have data that are extracted from a constant function or a linear function, then the P-spline is exactly that function. Then they conserve the two first moment, which means the mean and the variance of the data, and they do not show boundary effect like other smoothers do. And okay, but P-spline, as proposed by Ehler and Max, are only a model for polynomial splines, in particular for cubic spline, but then they were extended to a higher degree. Now, I want to go beyond P-spline and construct a class of function which is based on hyperbolic polynomial splines, and this is why I call them HP splines. I'm going to explain you, first of all, the motivation of the study of this new model and how we can construct them and some numerical results. Okay, so let's start with the motivation. Our motivation was the following. We want to define a model which is data-driven for data analysis of data that are of exponential type. And because we know that these data are frequent in applications, like, for example, epidemic growth patterns or nuclear magnetic resonance studies. So we know that there are situations where we have a set of data which is noisy but obtained originally from a function which is the weighted sum of exponential polynomials. And then if we have data that are somehow related to a function of this type, a polynomial spline is not the best to be used. So our idea is to substitute polynomial splines with exponential splines, but in particular exponential with a real exponent. So these are quite often called hyperbolic splines. And in case we also consider a possible polynomial terms, they are called hyperbolic polynomial splines. But I'm going to show you in a moment the specific spline space I'm considering. And then construct an optimal basis for this type of spline spaces and generalize the constructive idea that led to P-splines. Okay, our approach can be applied to any type of exponential splines, but we consider in particular a four-dimensional hyperbolic polynomial space, which is the equivalent of cubic splines in the polynomial situation. So the space we consider is this one that I called E4 alpha. Alpha is the frequency of the exponential, and we see that this is exponential and polynomial exponential, and also we consider the space E2 that consists only of one possible exponent. So, for example, only positive or negative, and these are the null spaces of some differential operator that I call with this symbol L2 and L2 star L2. We consider splines with segments in this space. In particular, we construct an optimal basis for the spline spaces A4, consisting of functions of this type. They are bell-shaped, compactly supported, based on 5 knots, uniform, C2 regular, and with segments, the elements, colored elements that you see here, that are in the space A4. And this space is, the spline space is capable of reproducing A2 only, not A4. But this is quite similar to the polynomial situation. We know that B-spline, they are capable of reproducing only linear polynomial, not cubic polynomial. Okay, then we apply the same strategy. So we considered first a penalized least square problem involving integral and derivative, and then substituted the derivative with the discrete operator and exploit the specific property of the basis in order to pass the difference operator from the basis to the coefficients. And of course, I cannot give you all the details, but working in algebraic way, we end up with our minimum problem that defines the hyperbolic polynomial penalized splines, HP splines. And for this particular space, of course. And these splines, the nice property they have is that whenever alpha is set to 0, so if we take the frequency parameter 0, we end up with cubic splines, polynomial splines. So HP splines reduces to P splines whenever alpha is set to 0. From a practical point of view, we have to solve a linear system to get the solution, and the matrix associated with linear system is structured, and this is due to the compact support of the basis. The property these splines satisfy are the generalization of the property of the P-spline. P-spline can fit a constant and linear polynomial. In our case, we can fit exactly the E2 alpha space. And similarly, while the polynomial P-spline conserve polynomial moments, we preserve exponential moments. And here you can see this class of function in action. I am proposing you 4 tests. The first test is a kind of benchmark on a classical data set, which is called the motorcycle data set, very much used by statisticians. And in this picture, you see the data in red, and in black the HP spline, and in magenta the P spline. And we see that there's not much difference. And this is something that we expected, because there's no prior information on the data that somehow link this data to an exponential trend. So the two models behave similarly, but in case, for example, we deal with a synthetic data set obtained by adding some noise to an exponential function, here you see the exponential function, what we get in black is the HP spline, in magenta the P spline, and they behave differently. And we believe that our model is capable of following the data better. This picture corresponds to the smoothing parameter 0.1, and this one to the smoothing parameter 1. Another example is the application of our model to experimental data corresponding to the coal production in Nigeria. And the production of the coal in Nigeria has an exponential trend. These are the data in red, and we see that our model in black is following much better the trend of the data rather than P-spline. So we were quite satisfied by our model. This last test is to show you that our model can manage also particular configuration, like the one that present an outlier. For example, this was configuration, many data here and a single outlier, and the model is quite responding. Okay, so we were quite satisfied, but the first a criticism that we got from the referee was how you choose alpha, so the frequency parameter, because this should be related data. Indeed, so the last part of my presentation and the last paper, we tend to choose it in a good way, because it can help to better capture the trend suggested by the data. Just to give you an idea, here you can see in this picture, for example, we were dealing with a set of data corresponding to infections by coronavirus, and we tested some possible, our model with possible different choices of the frequency parameter. With alpha 2, we got very bad wings, so very bad behavior. Alpha 1 was satisfactory, but looking closer, we realized that there was still a kind of oscillation behavior. And with alpha 0.2, we realized that our model was the best. So the choice of alpha is indeed a critical problem. So how can we choose alpha? We investigated in our last paper the impact of alpha to control the perturbation of the solution. And we propose a criterion to dynamically set alpha based on the data and the sensitivity of the model with respect to perturbation. To do that, we looked at our problem, so our minimization problem that lead to HP spline as a Tikhonov regularization problem in general form. This is quite simple. So we wrote it in this way, and we for the Tikhonov regularization problem there are several theoretical results, and we found one result, a theorem in Hansen book that investigate the impact on the solution of a Tikhonov regularization problem on a perturbation of the data. And in this theorem that I'm reporting here, there is a so-called condition number that is linked to the matrices involved in the formulation of the problem that we decided to use it for the selection of alpha. Why? Because we tested the computation of k for several functions. For example, look at this function here is a pure exponential function, and we realized that the minimum of this condition number is attained very close to the perfect possible alpha we can choose in this case. For example, for data coming from this function, of course, the best alpha would be -1. And we realized that looking at the minimum of kappa, we could get an idea of the best alpha. So we based our procedure for parameter selection on this observation. Not only this, of course, we performed several tests, numerical tests, but we realized that the computation of this condition number is quite expensive, in particular because it involves a generalized singular value decomposition. And then we worked on an estimate for this condition number that we denoted by k tilde, which can be computed directly, and decimizing the computed or approximated condition number. Here you can see the idea we use. So this would be the condition number as a function of alpha for a particular test we consider. No, for the function I showed you before. And we see, and this is in blue the approximated condition number. They both have the minimum at the same value of alpha, which is indeed -1. And so for this test, there's no difference of minimizing the approximation k tilde or k. And we tested, of course, on several other examples. So we realized that minimizing k tilde produce a very good choice of alpha for several types of function. For example, in this case, we considered the rational function, and here is the result of our HP spline, which is very good. So the selection of alpha was very good.
Yeah, of course, if you want, I can send you the slide.
Sure, ma'am. On such an amazing note, let's begin the event with a virtue of melody. So I would like to call Shruti Sucheta Meher Didi and Sasmita Mishra Didi on stage to present a beautiful song.
Thank you, Mr. Madam.